Hey guys, welcome back to chapter 19, Electrochemistry. So now that we have been introduced to the Voltaic cell, excuse me, we're going to talk about a few more items that has to do with the Voltaic cell. So first we're going to talk about ways that we can do a shorthand, because we're lazy chemists, right? So we're going to do a shorthand of a Voltaic cell. And then we're going to talk about how we can quantify a Voltaic cell, so how we can put numbers to this. So first, our lazy chemist shorthand. So electrochemical cell notation. So we use something called a line notation. So a line notation is just a compact way to represent electrochemical cells. So by the end of this lecture, you'll be able to look at an electrochemical cell and write out a line notation, or look at a line notation and be able to expand that to an electrochemical cell. So that's something you'll be able or want to be able to do. Okay. So here's the general format. So the format is going to be electrode, electrolyte, and those would be the same. So it would be maybe like zinc, then the aqueous zinc. So they would be the same metal. So electrode, electrolyte, electrolyte, electrode, and then this double line here is kind of a symbol of the electrons going from one side to the other. So this would be one half cell, double line, the other half cell. Electrode, electrolyte, electrolyte, electrode. Okay. These electrodes are very specific, so we can't just pick any electrode and put that first. So the general rule of thumb is anode, oxidized, reduced, cathode. So exactly how you would see it in the picture. So the half cell over here, you'd have your anode and then your aqueous. And then go to the other side, you would have your cathode and whatever's being reduced. So again, we're still watching the flow of electrons from anode to cathode. Okay. So let's look at an example. So here's an example of a cell that we have seen before. So let's just break this down and see if we can draw the electrochemical cell line notation. Grab my stylus here. All right, so first we need to decide what's the anode, what's being oxidized, what's the cathode. So zinc has an oxidation number of 0. This copper would have an oxidation number of +2. Go to the other side, this zinc would be +2, this copper would be 0. Okay, so looking at zinc, it goes from 0 to +2. So that's losing electrons. That's going to be what is oxidized. And copper goes from a +2 to a 0, and that number is going down. So that is what's being reduced. Okay. So then let's draw our two half reactions. So we're going to have zinc solid becomes zinc ion aqueous, that's our electrolyte. And then we're going to have a copper aqueous to copper solid. Oops. Solid. This is 2+. And this is our, remember, oxidized, and this is our reduced. Okay. All right, so now that we've decided what's being oxidized, what's being reduced, we also have shown what's the anode and cathode by doing that. So whatever is being oxidized, that's the anode. Whatever is being reduced, that's the cathode. So to do the line notation, this is what it would look like. So first we would do our anode, which is zinc. We'll draw a single line. Then we would do our electrolyte that's associated with the oxidation. So the electrolyte associated with that would be the zinc aqueous. Two lines to separate the two half cells. So we go to the other half cell, we do the electrolyte or whatever was reduced. So is being reduced, so 2+. And then a single line, and we write our cathode, which is the copper solid. That's it. That is the line notation for this particular cell. Let me give you a clean version of it. So that's what it looks like. That's the line notation. Okay. So see if you guys can pause the video and draw the line notation for the following reaction. All right. So the first thing that we need to do is break this up into the two half reactions and determine where the oxidation reduction is happening. So we've got manganese, and then that becomes a solid, manganese. And we've got lead, and that becomes aqueous. Okay. Looking at our oxidation numbers, we've got manganese is a 2 plus. Over here, it's a 0. So plus 2 to 0. That number is going down. That's our reduction. And then lead is going from 0 to a plus 1. So that's going up. That's our oxidation. Okay. So again, once we have our reduction, our oxidation, that also gives us our anode and cathode. So where things are being oxidized, that's our anode, and where things are being reduced, that's our cathode. So the line notation is going to be anode, electrolyte associated with that anode. 2 lines to break apart the half cells. Then we're going to have the electrolyte associated with the cathode. And then lastly, the cathode. So, and I didn't put aqueous here. So that is the line notation for this reaction. Okay. The next thing that we're going to talk about is how to quantify these voltaic cells. So just a little definitions here. Again, probably information that we've never seen before. So we want to make sure that we lay a solid foundation to build upon. So we're going to be calculating something called electromotive force, or EMF. So EMF is going to be the difference in potentials that result in the motion of electrons. So we're going to look at the potential in one side of our cell. We're going to look at the potential in the other side of the cell, and we're going to look at the difference between those. That difference is what is going to dictate if electrons flow and which way the electrons flow. Standard cell potentials is the potential difference between the two electrodes in a voltaic cell. And again, we're using standards because one, we can just read a chart rather than doing an experiment to get the information. And two, it's just a little bit easier, a little bit more straightforward. Standard conditions, remember, are just room temperature, 1 atm of pressure. So the conditions that we're probably going to be working in anyway. So here's an example of a standard cell potential. So what they did here is they took the difference between zinc, the anode, copper, the cathode, and when we looked at the difference between those two, we see a standard cell potential of positive 1.1. And since we are talking about electricities and we are talking about currents, we are using the unit volts. So that shouldn't be surprising. When you're dealing with electricity, you're always talking about voltages, right? Okay. So what is this EMF? What is this standard cell potential measuring? Well, it's the overall tendency of the redox reaction to occur spontaneously. So when we get the E cell potential, that's going to tell us, is this a spontaneous redox reaction? So will this happen without outside influence? Or is this a non-spontaneous redox reaction where it's not going to happen unless we give it some assistance? So just another way for us to monitor the spontaneity of these reactions. Okay. So calculating the standard electrode potential. So we're going to need the standard electrode potential of each of the individual electrodes, okay? So just as a reminder, the anode is kind of the starting place. It's where electrons are leaving, and that's where the oxidation happens. And the cathode is our ending point, so that's where the electrons are traveling to, and that's where our reduction happens. So remember, if we quickly draw a voltaic cell, our anode, well, we have to show that the flow of electrons is this way. Our anode would be over here. Our cathode would be over here. Should be submerged. And this is where things are oxidized. This is where things are reduced. Okay. So it's important that we know which way the electrons are flowing. And what we're going to do is we're going to look at the difference between the cathode and the anode, and the difference in those standard potentials will be used to calculate what is the potential for the entire cell, for that whole battery. So here's an example of a chart that shows us the standard reduction potentials for lots of different half reactions. I've highlighted 2 here because we're going to talk about that zinc copper voltaic cell. So I've highlighted the numbers that we're going to use for that zinc copper voltaic cell. Okay. So the standard potential for the cell can be found through the following equation. So it's going to be cathode minus anode. So again, we've talked about this from Gen Chem 1. When we look, when we look at the change in when we look at the change in anything, so change in temperature, it's always final minus initial. And when we looked at change in enthalpy, it was still final minus initial. We just called it products minus reactants. And now that we're talking about an E cell potential, we're still doing final minus initial. We're doing cathode minus anode. Okay, so electrons always travel from the anode, that's the initial, to the cathode, that's the final. So we're still with the same theme, final minus initial, cathode minus anode. All right, so now that we know what voltaic cell we're studying, we've got the line notation, which helps us with breaking that apart into its 2 half cells. It also helps us with identifying anode and oxidation, cathode and reduction, okay? Then we would go to a chart and we would see that the potential for the copper is going to be 0.34. And we see that the potential for the zinc is going to be a negative 0.76. Okay. So to determine the potential for this entire cell, we're going to take, remember we take cathode minus anode. Okay. So our cathode is going to be this copper over here where things end. So our cathode is 0.34 volts minus the anode, which is the zinc, negative 0.76 volts. So two negatives essentially become a positive. So when we add these two numbers together, we get 1.10 volts as the standard potential for this half cell. Okay. Something else to point out here is the fact that your anode will always be lower in potential energy. So our electrons are going to flow from this negative or the smaller number to this positive or the bigger number. So that will always be how things flow. If you can't see where the anode and cathode is, look at the numbers. The lower number will always be the anode. Okay. So what I want you guys to do now is take a few minutes and calculate the cell potential for this voltaic cell. All right, so the way that it's written, this is going to be our anode over here, or our oxidation. Woo! This is going to be our cathode over here, or our reduction. Go to the chart. Let's look at the potential for aluminum. So the potential for aluminum is negative 1.66 volts. Potential for nitrate. So it's a little bit harder to see because we've got those hydrogens in there that helped us with balancing. But here we see the nitrate becoming NO, and we see that the potential is 0.96. So again, the lower number is the anode, the higher number is the cathode. So to calculate the cell potential, we're going to take final minus initial, cathode minus anode. Okay. So let me grab my calculator here. We're going to take 0.96 minus negative 1.66, and that's going to give us a potential of 2.62, and remember our unit here is volts. All right, so that is calculating cell potentials. So what I want to do now is just summarize this chapter. So we've come to the end of the information that I'm going to test you on. So now I just want to summarize everything that we've talked about, kind of give you a visualization. So here's a summary of our voltaic cell. So keep an eye on the flow of electrons. So all of this would be reversed if I gave you a picture. Whoopsies. If I gave you a picture that said electrons are flowing this way. So always first identify which way the electrons are flowing. So since the electrons are flowing from left to right, the things that we know is this is our anode. Okay, electrons are leaving the anode. This is where oxidation happens. And we also know that the potential energy is lower on this side, so lower potential because we flow from low to high. Our electrons are flowing to the cathode, so that means over here is our cathode. That's where our reduction takes place. And this must have a higher potential because that's where our electrons are ending up. Okay, so just a quick summary of the voltaic cell. Here's a summary of this chapter. So these are the things that I'm going to test you on. There's so much more in this chapter that we didn't get an opportunity to cover. So I want to just be clear on what it is that we did cover. So just remembering redox reactions, so identifying oxidation, identifying reduction, oxidation numbers, balancing redox reactions. So that's where we go through and we split it into two half reactions, make sure the atoms are balanced, make sure the electrons are balanced. Then we applied that to a voltaic cell. We did a shorthand of the voltaic cell, so that was the electrochemical cell notation. And then we calculated the standard potential for those voltaic cells. That is the end of information for chapter 19, and that is the end of information for general chemistry 2. I hope you guys found these videos helpful.